near as dynamic a constant force spring. So you have very even support regardless of the amount of force put on it. I'll say no more than that as far as braziers are concerned. These, however, are some of the applications I've developed using shape memory alloy, and this is a rather non-exhaustive list. I've got a drawer full of various things. Aneurysm grafts into the for the treatment of abdominal aortic aneurysms. One of the companies I formed, which floated on the London stock market 2001 and is now international, set up in the USA. We're selling large numbers of these. It's been rather successful. Another picture of it in the middle, the anti-kinking properties of this to negotiate tortuosity and angulation in the vascular system. Sutureless anastomosis, that means joining blood vessels together without having to suture them. These are hose clips, Jubilee clips for the more old-fashioned of us. Very successful. Little general purpose gripper for soft tissue, gripping it automatically. You heat the thing up and the two ends of the gripper just come together. Modulus matched bone plates on the at the end there, and again other orthodontic correction devices. This incidentally was also the subject of another European venture with the Eureka program, successfully completed. New methods of minimally invasive treatment for the replacement of aortic and mitral heart valves, which is something very current, something I'm very involved with at the moment. The reason I came out here is ESA gave me 13 cows, or ESTEC gave me 13 cows, and the cows are KAUs, kilo accounting units. This is before the days of the euros. 13 cows equates to about £9,000. Quite remarkably, for that technology transfer that the ESTEC facilitated, I was able to design, develop, make and test those devices on the extreme left-hand side at the top, bone staples. These are little devices, the two legs of them come together, and if you have a fracture of some kind, I've shown some images of some of the technology being applied here. If you have a fracture, you can put these staples into pre-drilled holes into the bone. Obviously, this is a surgical intervention, not a minimally invasive one. And the two legs come together after they've been deformed and pull the two bone ends together, satisfying the two essential requirements in bone fractures. That's bone fracture reduction and stabilization. So I was able to design, manufacture and test and run 2 human clinical trials. This is just before the barriers went up as far as the regulatory conditions changed in 1996. In those days I was able to get an old coat hanger and sort of bend it up and put it in someone to try something out. I'm definitely not allowed to do that now, hence the £9,000 which facilitated this, which is towards a miracle actually for that sort of sum of money, has been very successful. Bone plate again, that's hundreds of thousands of those are used all over the world. Shape memory alloy gives you automated fracture reduction and modulus matching, which is very, very important. The metal has a similar E modulus to the bone, not identical, but it's much, much closer than the alloys used at the moment. Another device, this is a staple, a rather handsome product. I guess I would say that because I invented it, but it's handsome in terms of its commercial activities at the moment. This is to fix tissue to tissue or grafts to tissue or any combination. It's a bit of super elastic, little sort of gull wing shape there, which is completely repositionable if the surgeon takes a suboptimal choice of placement. It's brought into a small tube, a plastic tube in this case, deformed. Those two legs then straighten and they're sharpened at the end. You position the end of the device near to the thing you want to effect some fixation, deploy the handle, you push it out, and the thing gives a compressive force and locks everything together. So it's a completely disposable, being sold in quite large numbers at the moment. what it might do here is indeed fix one of these. This is another one of my devices for the treatment of aneurysms. That's a schematic of actually what happens. Polyester tubular structure using embroidery and sewing techniques, fabricating techniques. On the outside is a nitinol or superelastic wire. Again, that's sewn into place. The blood flow now is excluded from that saccular geometry. The danger here is that that may rupture or burst, and that's 80–90% fatal condition. So you need to put one of these in before you get to this sort of position. The superelastic material is there because you put this into a catheter approximately 6 millimeters diameter. That's around 25 millimeter diameter, which approximates your aorta, if you like. So it's squashed into this little tube for minimally invasive introduction, deployed, and the superelastic material then springs out, giving it body, so to speak, and helping it to seal at the proximal, or the top and the bottom end. Okay. My last slide here. The reason I've got a panda here is another ESA story, which I'll just relate very quickly to. I developed, during the biosample and Eureka ventures, a tiny little peristaltic pump, which at that point in time was probably the smallest in the world. They've certainly been superseded by others. And I got a call from an endocrinologist at Royal Holloway College that had a project with Washington Zoo. As you know, the female panda comes into estrus possibly once a year, and sometimes I think they hang everyone up and do it every 5 years. But anyway, that's one of the reasons why there's a bit of a world shortage of pandas. So what this endocrinologist wanted to do was to put a tiny pump and a reservoir of a hormone which would artificially bring the female into estrus. And the whole experiment was, there's cages, there's the female in one with this mechanism inside her, and the male at the other side of the cage, and they'd introduce the hormones and then remove the barrier between them and let them get together. Now, what actually happened here, this was entirely successful. My brief was to put a pump, a reservoir, and a timer mechanism in a 19 millimeter silicon tube that could be implanted in the musculature on the back. And this was done. I took apart a perfectly good Seiko watch and did some very fine soldering and reconnections to make the timer into it, and a small battery went into the whole thing. Anyway, the surgery was done, and they set the two pandas up. However, shame on the biologist, because the system actually worked. The female was sort of, can I say, climbing the wall, trying to get to the male. However, what they hadn't accounted for is the male is also timed somewhat to the female, and they did nothing with it. So the male just hung around at the back of the cage eating bamboo and not really caring too much at all, and nothing happened. Anyway, let me call that a small success as far as the female is concerned, and leave you with that thought. May I give some acknowledgements to some of these people here, particularly Brunel University, Brunel Institute for Bioengineering, ESA and ESTEC, of course. I guess it's a bit egocentric of me to give a thanks to Anson Medical, but Lombard Medical, Anson Medical, Intrinsic Devices, Memory Safe, and so forth, Rowenta, the KTN, and last but not least, the Technology Strategy Board. Thank you very much.